On page 12, we're going to begin our first real contextual problem, a problem in which the second fundamental theorem really means something in a real life example. It is important to note that everything in this accumulation section is really derived from the second fundamental theorem. So that's why up at the top of page 12, there's a quick little blurb there that essentially summarizes what I just said at the end of the previous video. So if you watched that video, I don't think you need to read and analyze this paragraph because it's essentially restating what I've already spoken of. But if you want to read it, especially if you've been skipping through videos and not necessarily making it to the end, this is a good paragraph to just formalize the connection and to understand that we're really just doing second fundamental theorem problems again, that we're trying to connect the effect of taking an integral and taking a derivative and understanding what that means. So in question number 3, we're going to deal with, as I mentioned, a real life situation, something for which the integral actually has a real life connotation. So in question number 3, let's look at this graph, which is of little f of t, and I want to make sure that that part is obvious. This graph is going to represent little f of t. If you're wondering why I'm making an emphasis to say the word little there, it's because I'm previewing some of the rest of the question and noticing there's also going to be a big F in the question, which is a ridiculous choice on the part of mathematicians, but here we are, 26 letters in the alphabet, and we chose to use the same letter, just the capital version, to represent a different quantity, but that's okay, here we are. So little f is going to represent the graph, and anytime I see the phrase little f of t, I'm going to think graph, because that's what they're giving me. They're not really giving me an equation or a function for little f, they're giving me a graph instead. Now it talks about the fact that little f illustrates the rate of snow accumulation in the local mountains. So this is a graph of rate. Now it's important to note this is not a graph of snow. This is not telling you how much snow fell. It's a graph that's telling you how fast snow fell. So it says, for instance, at t equals 1, snow is falling at a rate of 3 inches per hour. So at t equals 1, which would be the 1 as the x coordinate, so to speak, or the t coordinate, if you think of it that way. At time 1, the snow is falling at a rate of 3 inches per hour. So that point on the graph represents how many inches per hour the snow is falling at. So the speed of the snowfall. At t equals 3, so I'll think about this next point. At t equals 3, snow is not falling. It is not snowing at all. And you can tell that makes sense. The rate of snowfall would be 0 inches per hour. Nothing's happening. At t equals 4, which would be this point here, snow is melting at 4 inches per hour. Negative rates mean that the snow is essentially disappearing. Snow is melting. The snow is the opposite of falling, which doesn't really make sense in context, but if the snow is actively falling at a positive rate, then that means it's building up and building up and building up, dare I say, accumulating. So if the snowfall rate is negative, that means the snow is doing the opposite of accumulating, it's melting away. So hopefully we can kind of get that context here and understand that the x-axis, so to speak, is measuring in hours what's happening to the snowfall, and the y-axis, or the f of t, is measuring at how many inches per hour the snow is falling. So it's a rate. Now, in letter A, it says to let big F, there's a choice, represent this integral. So, okay, big F is this function. Big F is this thing here. It says, what does big F represent in this scenario? Now let's think about this for a second, because there are two different interpretations that you can use, and maybe one of them will make more sense than the other. Here's the first thing I'm thinking of. Big F is an integral, which means big F is an area. An integral is an area, right? We've made that association before. Big F is an area. So let's think about these areas. Now, I don't really want to find all these areas, I'm not going to lie, until I have to. I'm going to avoid that as long as I can. But let's just think about one of the areas. Like maybe if I just focused on, for a second, that little tiny rectangle from 1 to 2. What if I just focused on that for a sec? If I found that area from 1 to 2, The base of it would be measured between 1 hour and 2 hours, so the base of it would be in hours. And then the height of my rectangle, whatever that is, would be measured in inches per hour. And I'd be finding the area by doing base times height. Now, whatever those numbers are, the number of hours in the base is going to cancel the bottom of this inches per hour in the height when I multiply them. So hours would cancel, leaving us with inches. So that means that the area that I calculate represents inches as its units. Think about that for a second. That means that every area that you calculate represents how many inches of snow have fallen. So the area from 0 to 1, that's how many inches of snow fell from time 0 to time 1. The area from 1 to 2 is how many inches of snow fell from time 1 to time 2. So the area total from 0 to 8 must represent the total number of inches of snow that fell from time 0 all the way to time 8. So a quick analysis of area tips me off that big F, the area problem, represents, and I reiterate, the total number of inches of snow that fell. Or, if you want to summarize it, the total amount in inches of snowfall. Now, if that interpretation doesn't make sense, perhaps this one will. If we think about big F as an integral, think about the fact that it's an antiderivative of inches per hour. Remember when we always used to talk about units when we did like velocity problems and stuff like that? Like when you have a velocity and it's usually measured in, say, feet per second, think about going backwards from velocity. If you have a velocity, which is normally a derivative, that gives you units of feet per second, and you go backwards to the position function, what would the position function be measured in? And we usually tell ourselves things like, oh, well, the position function would be in feet, because the derivative would be feet per second, so going backwards, feet per second, would be feet. So if you're given a derivative, if you're given something like the velocity, the original function must be measured in the original units, feet. So some people would think of this and say, well, this is kind of like a derivative, inch per hour. So the original function must have been inches. And that makes sense to them. That's the same way that velocity and acceleration and all that makes sense. Now, some people don't think that way at all, and their brains are like, what? So that's why I recommend for those folks using the area as a more successful interpretation. That if you use the area and use the units of area, that probably will help reinforce to you why the units of this answer in letter A are going to be inches, and why letter A represents the total amount of snow that has fallen, or the total number of inches of snowfall. So you can phrase it however you want to, but now we know that this total is going to be the number of inches of snow that fell. And I'm purposely writing it two ways in case one interpretation makes more sense than the other. Now, let's see if we can put this in concrete terms. In letter B, it says to complete the table. That's a familiar looking table. We've done this before, so I'll do a quick example just to set you off on the right track in the hopes that you can do the majority of this table on your own. Just to reiterate, you have a choice here about how to do this on either scratch paper or whether you can just kind of juggle it all in the picture. But the first spot is the integral from 0 to 0 of f of t dt, and then you can ask yourself, okay, what does that mean? Now, I don't have the option of doing a proper calculus antiderivative here because I don't have a function for little f. The only thing they gave me about little f is this picture. So that's the only way I can interpret this info. I have to use the picture in order to do this integral, which means I have to treat it like an area because that's the only information visually that they're giving me. So the area is going to be from 0 to 0. Well, that's trivial because if I start at 0 and end at 0, the base is going to be 0. The height is going to be 1, but who cares? 0 times 1 is an area of 0. So I'm going to definitely think about this as an area problem. And that means I'm going to be thinking of each of these integrals as individual areas to calculate. So the next area that I need to calculate is the area from 0 to 1. And notice I keep saying area to emphasize, because that's the only way I can do this problem. Now I want the area from 0 to 1. So looking at my picture, from 0 to 1 would be this little region that I'll shade in here. You'll of course have to ask yourself what's the most effective way to calculate that region. You could look at it as a sideways trapezoid, or you could see it as a rectangle plus a triangle on top of it. Doesn't really matter, but I'll just think of it as a trapezoid just because that seems to kind of occur to me to do quickly. That integral then, or that area, would be a trapezoid sideways, so its bases horizontally would be 1 plus 1, 2, 3 times its height, which would be 1, and then half, because that's the formula for the area of a trapezoid. If it confuses you to do it as a trapezoid, do it as a rectangle of 1 plus a triangle, base times height divided by 2, and then just add those two separate regions together. But either way you go, you should end up getting that the area of that region is 2. No matter which way you calculate it, the area is definitely 2. So in my table, I'm going to record that the area from 0 to 1 is 2. Then I'm going to do the next one, the area, or the integral, from 0 to 2. Now, of course, I can piggyback on the answer that I've already found, so I'm not going to reinvent the wheel here. What I'm probably going to do strategically is find the area from 0 to 2, which will be this region I'll highlight in pink, or sorry, from 1 to 2, which I'll highlight in pink, and then I'll just add that to the area I already found from 0 to 1 to get a total. So the color coding might end up helping here. The area from 1 to 2 is a nice little rectangle. So base of 1, height of 3, that means this area is going to be 3. And that means in total, because again, remember the integral that I'm trying to find is the integral from 0 to 2. That's the total region from 0 to 2. So that would be the first green space, which is 2, plus the pink space, which is 3, for a total area of 2 plus 3, or 5. So notice this time you're not just finding one specific area, you're finding the total of all the areas from 0 to wherever your ending space is. So take some time if you can to just make sure that you can conceptualize this. I'll do one more to get you off on the right track here, and it's going to be the area from 0 to 3 to make sure that we're okay. The integral from 0 to 3, or the area from 0 to 3, means that I have to take into account the first two sections I've already done, plus this little sliver that represents a new little triangle. So this new little triangle would be a base of 1, height of 3, so base of 1 times height of 3 divided by 2 would give me 1.5. So there's my next area is 1.5. I like to just record them so I can see them. Some people even go so far as to color code so they can tell which areas correspond to which parts of the picture. Do whatever you want to do here to organize yourself. But that means now, to complete the table problem, I have to do the total area from 0 to 3, which would be 2 plus 3 plus 1.5, which appears to be 6.5. Now I promised I would just finish there and then have you do the rest, but I'm instinctively inclined to do one more section after this because I notice after 3, things get a little more interesting. Let me do one more just to make sure I don't throw you off. Let's go all the way to 4. I'm going to highlight that little blue triangle there so you can see why this is a special scenario that I do want to take into account. This blue triangle is going to have a negative area. And if you're reminding yourself of why it's possible for an area to be negative, remind yourself then that this triangle has a base of 1, positive, because it's going to the right, but a height of negative 4, because the height's going down in the negative direction. So base times height divided by 2 would be negative 4 divided by 2, which is negative 2. So that blue space has an area of negative 2. And when I go to accumulate that, in other words, when I want to find the total area from 0 to 4, total again refers to accumulation